To better understand the intensity in interference patterns, I suggest you to watch the two previous videos. One is called Interference and the Young's Doubleslit Experiment. In the double-slit experiment, we saw that the interference pattern produced by the coherent light from two slits, S1 and S2, and produces series of bright and dark fringes if the two monochromatic waves of wavelength lambda are in phase at the slits, and the maxima, which are the brightest points, occur at angles theta given by this expression of d sine theta equals m lambda. Let's put here maxima here, which is the bright fringes, and d sine theta equals m plus 1/2 lambda for minima, which are the dark fringes, darkest points. Let me just add here brightest for your reference, brightest points for the maximum. Let's now determine the intensity of the light at all points in the pattern. We know that the intensity of the light at any point is proportional to the square of its wave amplitude. So if we assume that the two sources have the same amplitude E and the same polarization, then we can write intensity equals 1/2 epsilon naught C E squared that we learned earlier, or it could be written as a E squared over 2 mu naught C, or it equals 1/2 square root of epsilon naught over mu naught E squared. I have another video on this topic, so if you forgot this, you might want to pause here, go watch that other video and come back. The electric field E at any point P will be the sum of the electric field vectors of the waves coming from each of the two slits, E1 and E2. So I can write vector E equals E1 plus E2. Since E1 and E2 are essentially parallel on a screen far away compared to the slit separation, the magnitude of the electric field at angle theta, which is at a point P, will be E theta equals E1 plus E2. So both E1 and E2 change sinusoidally with a frequency of C over lambda, but they differ though in phase. So I can write that as E1 equals, let's put E1 at T equals E cosine omega T plus phi, and E2 T equals E cosine omega T, where obviously you already figured out the phi is the phase difference, and it depends on the angle theta. Let's now determine the phi, the value of phi depending on the angle theta. So phi depending on angle theta. So let us look at the center of the screen at point 0, which is on our picture is right here. Okay, where the difference in path length from point P to S1 and S2 is the same. So I can say phi at angle 0 equals 0. So there is no phase difference. But if the difference in path length from our point P to S1, so we have this, let's call this one R1 and this one R2, the difference of this two, R2 minus R1 equals half a wavelength, which equals d sine theta, then the two waves are exactly out of phase, so the phi should equal pi or 180 degrees. So if R2 minus R1 equals just the lambda, which is d sine theta, the two waves have a phase difference of just 2 pi. So if we want to write this in general, I would say phi over pi equals d sine theta over lambda. Oops, I made a tiny mistake here. It should be 2 pi, not pi. So I used these two expressions to come up with this relationship. Now, if we want to determine our E theta, that equals E1 plus E2, we need to use a phasor diagram. So let's recall E1 had a phase of omega t plus phi. The other E2 has a phase of omega t, but they both have the same amplitude E. That means our vector has to have the same length as E. At E1 at the angle omega t plus phi, E2 at the angle omega t. So let's just draw that here. So let me put my vertical and horizontal, and then I'm gonna start with the E2, where the vector has a length of E at angle omega t. So this will be my E cosine omega t. Now if we make another horizontal here, so I can build head to tail the second, actually the first E1, so that will have in let's try to see again this angle omega t here. Okay, and then we need some little phi angle, so it will give us same length vector. It's a little bit longer than the same length, so hold on. Okay, so this would be again the length to be E, and the angle here would be the phi. So if we draw here, this would be from E cosine omega t plus phi. Okay, let me just highlight that portion of the vectors. So this is E cosine omega t plus phi, and this one is my E cosine omega t. Now head to tail method, from the beginning to the end will give us the resultant vector. So here's the resultant, and it would be my E at point P, or E theta. So to find now the EP, we're gonna use law of cosine, and maybe you need to recall, or I can remind you. So if you have a triangle with sides A, B, and C, and this is the angle theta, then law of cosine says the C squared equals A squared plus B squared minus 2AB cosine theta. Okay, so now if I use this one, then I can really find the EP. So in my triangle, I have A equals E, B equals E, and C equals EP. And this theta, so the theta would be equal pi minus phi. Let's make that visible on our picture here. So this is pi minus phi right here. Now, considering all this stuff, I can write E p squared equals E squared plus E squared minus 2E squared cosine pi minus phi. And let's recall, if you have a cosine pi minus phi, that is the same as negative cosine phi. So my results for EP squared equals, so 2E squared minus, now it will be plus with this negative, plus 2E squared cosine phi. Now if I take the 2E, factor the 2E squared out, I will have 1 plus cosine phi. And from the trig identities, I know that 1 plus cosine phi is a 2 cosine squared phi over 2. And let's not forget our 2E squared here. And that is making it equal 4E squared cosine squared phi over 2 in parentheses. So let's recall that on the left side we had a EP squared, and if we take the square root from both sides, I will have EP equals 2E absolute value of cosine phi over 2. Okay, well, let's analyze this a little bit. When the phi equals 0, that means the waves are in phase. Then our EP equals 2 times E. As we would expect, the amplitude doubles up. When the phi equals pi, which is half a cycle. So then we have not in phase, or half a cycle difference. Then we would have cosine pi over 2 equals 0, which will lead us the EP equals 0, so you will have a 0 intensity. Now, if we recall what we have said in the beginning about the intensity, which is here, then I could say intensity at point P equals 1/2 epsilon naught C EP squared. So let me write that on the bottom, and then we will substitute the EP with the expression that we found. So I'm going to write intensity equals EP squared over 2 mu naught C, or equals 1/2 epsilon naught C EP squared, or equals 1/2 square root of epsilon naught over mu naught EP squared. So if we plug in this value, this expression in here, then for intensity we will get an expression of 1/2 epsilon naught C 2e absolute value cosine phi over 2 squared, which can be simplified to 2 epsilon naught C e squared cosine squared phi over 2. Now, maximum intensity happens when phi equals 0. Then I can write I max equals, we can call it I naught, which equals 2 epsilon naught C e squared. So this would be maximum intensity. For intensity in general, then I can rewrite the expression of I equals I naught cosine square phi over 2. As we can see here, intensity depends on the phi, and it varies between 0 and maximum intensity. So if we want to find the average intensity, so let's call it I average, then we have to take the average of cosine squared. So if you take the cosine squared phi over 2 average, that is 1/2. Then I could say average intensity equals half of the maximum intensity, or simply it could be epsilon naught C e squared. If we take carefully, take a look at this expression carefully, we'll see that the energy output from the sources didn't change, but it is redistributed. That is a very important notion to make. Now, going back to the phase difference between the two fields at any point P, where we said the phi over 2 pi equals d sine theta over lambda, or we could write path difference delta r over lambda. So we also said that the phi equals, we could write 2 pi delta r over lambda. And if you take a look, this 2 pi over lambda here is the wave number k. Then I can write phi equals k delta r. So now we have been always assuming that the material between the sources or the slits and the point P is vacuum. But what if it's other than a vacuum? Then we must use the wavelength in the material. So the wavelength usually in the material can be found by lambda n, which is the n is the index of refraction of that material, the lambda in vacuum divided by n. So hence the kn, the wave number k at that material should be equal n times k. Finally, substituting this expression that we found earlier, f equals 2 pi d sine theta over lambda into our intensity equation, and let's make sure that we just put here lambda n for a general case, and substitute this into our expression for intensity that we found, I equals I naught cosine square phi over 2. So let me write that down here. So I naught, pretty much what I'm doing, I'm going to substitute the phi into this expression. So I would get I0, I naught cosine square phi over 2 equals I naught cosine squared, so 2 pi d over 2 lambda n sine theta, where I can cancel the 2's out. Well, I forgot the 0, not in here, 0. So we said I max happens when cosine, this whole cosine thing equals 0, equals 1 plus minus 1, which means pi d over lambda n sine theta equals m times pi, where m is a number 0 plus minus 1 plus minus 2 and so on. Now if we cancel the pi's out, we will end up getting b sine theta equals m lambda n. Well, guess what? We already knew this, right? This was the condition for constructive interference. Now let's go back to our diagram. In this diagram, so the position of a bright band or bright fringe y, let's call it m, we know that could be written as ym equals r m lambda over d. Or I can write m lambda over d equals ym over r. So if you look at the diagram, y over r will give you the tangent theta, which is approximately, for small angles, could be estimated as sine theta. So only for small angles, okay? Let me just write here for small angles, tangent theta is approximately equals sine theta. Now if I plug this value of sine theta into my expression for I intensity, that equals I naught cosine squared pi d over lambda sine theta, and plug this value into here, then I can say intensity equals maximum intensity I naught cosine squared pi d over lambda times y over r. So this would be an expression for an intensity at any point on the screen. Now let's graphically visualize the points on the screen and intensities. I'm going to put the screen horizontally, and then I'm going to put the intensities on a vertical axis, where let's suppose this one is maximum intensity. So here I'm going to put the values of y, the distance of a point in the pattern. And then I want to do corresponding values for the phase difference, phi, and the corresponding values for the path difference, so which is d sine theta. So let me write it for you. Path difference So this is the 0, y, the central fringe, and then we go ahead and start with the path difference lambda, 2 lambda, 3 lambdas. That 1 lambda will correspond to phase difference of 2 pi, and 2 lambda will correspond to phase difference of 4 pi. 3 lambda will correspond to phase difference of 6 pi. And so for the r, we have the first one is a lambda r over d. For the second would be 2 times lambda r over d, and so on. So these points correspond to maxima. I'm just gonna mark my maximum points so I can easily draw, and then one maximum, central maximum here, here, and here. And minima will be the halfways. So it would be easier for me to draw if I mark this maxima and minima. Okay, now we would have a situation going like that. Minimum, maximum, minimum, maximum, minimum, maximum, minimum. Obviously my scaling is not very good because I'm doing it by hand, and so on. Well, there is one notion we have to make. This intensity pattern that we have expressed in our equations up here and in the plot that I just drew for you, assumes that each slit alone would illuminate the screen uniformly. This is never quite a true thing, though, as we shall see when we discuss diffraction later. So we will see that the center maximum is strongest and each succeeding maximum to each side is a little less strong. So pretty much you might want to imagine something like this. Okay, so a little bit less. So we will see this when we discuss diffraction. Thanks for watching, and obviously I'm going to prepare more, and looking forward to make a video on diffraction. Have fun and stay tuned for more videos.